Yesterday, in the last lecture, we have considered the various methods which are available to solve the numerical boundary eigenvalue problem posed by considering or by the description of radial and non-radial linear pulsations. We have discussed various methods, and we method, which is a shooting method. A shooting method means the perturbation problem or the differential equation is considered as an initial value problem, integrating from the boundaries towards the center of the integration interval, which has, in the case of a boundary value problem, the disadvantage that you have only part of the boundary conditions given, and the other part of the boundary conditions needs to be guessed and needs to be iterated. So there are in general, no unique boundary conditions no unique initial conditions for the integration of a shooting method from the boundaries. And this causes also not only the problem that these missing boundary conditions have to be iterated, but it also introduces in general for systems which are higher than second order, it causes numerical instability, in particular the parasitic growth problem, which makes them not suitable or makes them not applicable for higher order systems. Well, a solution of the problem is the so-called Riccati method. It is a shooting method which integrates from the boundaries towards the center of the integration interval with unique and unambiguous initial conditions. We have then convinced ourselves that our systems, the radial and the non-radial boundary eigenvalue problem, can be used or can be written in terms of the Riccati formalism, and we can apply the Riccati formalism to our problem. Okay, we ended up with the Riccati. We convinced ourselves that, for instance, the matrices contained in the Riccati formalism are maybe filled according to our needs with our coefficients, which are given by the perturbation problem we have derived, and in particular that the boundary value of the Riccati matrix is given in a unique way by the boundary conditions of the system. So the Riccati matrix has unambiguous values at both boundaries. There are no degrees of freedom, and we can use these unambiguously defined values of the Riccati matrix as unique initial conditions for the integration of the Riccati equation, which is a matrix differential equation which is no longer linear but which contains a nonlinear term. Okay, so we have overcome the ambiguity in the initial conditions. We have unique initial conditions, and we can now integrate the Riccati equation as an well-defined, unambiguous initial value problem from each of the boundaries towards the center of the integration interval. Okay, so if it is not possible to formulate the boundary condition within the framework or according to the definition of the Riccati matrix, we may also take the inverse of the Riccati equation of the Riccati matrix as a dependent variable, and we end up with a similar equation, with a similar Riccati type equation, simply by exchanging the role of the matrices A's and D's and B and C. So we can alternatively define V is S times U, and S In the case if S has an inverse, then S is given by the inverse of the Riccati matrix. And we obtain a similar or the same equation simply for S, simply by exchanging the matrices A and D and the matrices B and C. Okay, this is the strategy, and the question is now, how do we determine then the eigenfrequency sigma? The matrices A, B, C, D contain information about our stellar model, our hydrostatic stellar model, and they contain the parameters sigma, the eigenfrequency, and if we consider non-radial perturbations, then it also contains the parameter L, which is the harmonic degree. Okay, so let's start the integration both at x equal to 0 and x equal to 1, taking for this example, taking the relative radius as the independent variable, but you can also take it as an example for any boundary value, in terms of the independent variable x. So we have two boundaries here at x equal to 0 and at x equal to 1. Our boundary conditions give us a unique and unambiguous value for the Riccati matrix, both at the inner boundary and at the outer boundary. So this R is given by R in 0 and R out 0. And we can start with these initial conditions to integrate the Riccati equation. We perform the integration to some value of the independent variable, which we call the x fit. This is a in principle, freely chosen value to which we integrate our matrices R by integration of Riccati equation, and what we obtain is the final value from the integration from the inside. We obtain the matrix R in at the point x fit, and the integration from the outer boundary towards x fit yields the matrix R out at x fit. Okay, so we can freely choose this fit point. This might be important to determine afterwards, or might be this point can be chosen such as that the subsequent iteration can be done in a convenient way. So we are free to choose this fit point in the middle of the integration interval. Okay, how do we determine now the eigenfrequency sigma? Well, at x fit we require that the functions u and v, which we don't integrate, we don't know the functions u and v, we only know the Riccati matrix R. So we require that our functions u and v are continuous at the fit point. This is necessary because they have to satisfy a differential equation. They have to be differentiable. That means they have to be at least continuous at the fit point. Okay, this means that the integration, or well, we haven't done the integration of u and v, but suppose we did the integration of u and v from inside and outside, then of course the value of the integration of the component u from the inside has to be equal to that from the outside, and similarly also the value of the component v integrated from the inner boundary has to be equal to the value of the integration of v from the outer boundary. Okay, now we know by definition that u in is given by Riccati matrix integrated from the inside times v in, and this has to be, by this requirement, has to be equal to u out, which is given by definition by R out times V out. Now V out has to be, by the continuity condition, has to be R out times V in. That means if we compare these two terms, this term and this term. That means R in minus R out acting on V in is 0. This homogeneous linear equation only has a solution if the determinant of the matrix R in minus R out is 0. So we get as a condition for the solution, necessary for the solution, for the continuity of the variables at the fit point, that the determinant of the matrix, the Riccati matrix, obtained from the inner integration minus the Riccati matrix obtained from the outer integration has to be 0. Okay, well, Riccati matrix is a complex matrix, so this is a complex function of a complex variable. The only variable we have left in our system is the complex variable. Sigma is the complex eigenfrequency. So we are left with a simple, with one equation only, one equation, one numerically given equation. It's a complex equation of a complex variable whose zeros determine the solutions for the eigenfrequency sigma. So this equation can be used to determine now the eigenfrequency sigma. There is no ambiguity in the initial conditions. The only ambiguity or the only parameter of this integration is the eigenfrequency. And in the end, we obtain a complex function whose zero are the eigenfrequencies sigma. And it's gratifying that this procedure, this numerical strategy is in fact stable. Okay, so we have a function whose zeros determines the eigenfrequency. We did not need any information or any estimate for the solution. Nothing is required. The initial conditions are unambiguously defined. The coefficients of our matrices, the boundary conditions, are unambiguously defined. There is no information and no estimate on the solution, for instance, on the eigenfunctions, is required. Nothing. We just integrate the full system of equations. We don't need to have an approximation to the system. We don't need to solve an approximate problem to get an estimate for the eigenfrequency. We take the full system of equations and get finally a simple one-valued complex function whose zeros are the eigenfrequencies. So if we want to get an overview where the eigenfrequencies are, we simply have to integrate the Riccati equation for various values of the eigenfrequency over the complex plane, and we have to tabulate the determinant function. Okay, so example to get an overview where the eigenfrequencies really are. Well, we take, for instance, we could also go over the entire complex plane and tabulate the determinant function over the entire complex plane. For practical purposes, it's easier to go along some lines. Here we have taken a line parallel to the real axis, so we have a constant imaginary value, and we tabulate the function along this dashed line parallel to the real axis. But you could also take a line going at a certain slope through the complex plane. You are free to obtain an overview over the run of the determinant function in any other way. You could also cover the entire domain of the complex plane with tabulating the determinant function there. So it's a complex valued function of a complex variable given in terms of sigma r and sigma I. These are the quantities which we want to know. as an example how this might look like, is the modulus, the log of the modulus of the determinant is given along such a cut through the complex plane. And what we see here, we see pronounced minima in the determinant function here, there, and there. And these are the places which seem to be close to a real root of the determinant function. So if we take, for instance, these values as an initial value for the iteration, for the subsequent iteration, we might end up here with the eigenfrequencies which we were looking for. So the first overview over the run of the determinant function can be obtained by simply taking a cut through the complex plane and then tabulating the determinant function here. These dots, each of these dots corresponds to one integration and gives a certain value of the determinant function. And whenever the determinant function vanishes, we have an eigenfrequency of the system. So no iteration of any other parameter has to be done. The only iteration which is needed then in the end is to determine precisely the value of the eigenfrequency once we start from an estimate of the eigenfrequency obtained, for instance, by tabulating this function without any reference to any approximation or any auxiliary solving an auxiliary problem. This can be done for the full system of the equations. Okay, so for the precise determination, the determinant function itself may provide reasonable initial conditions or reasonable initial guesses. Questions? Everything is clear? Okay, now I have to comment on some problems here. The Riccati matrix may become singular during integration, so it may diverge. This is not a numerical error. This is a genuine property of the Riccati equation. If that happens, that means if the determinant oversteps some critical value, becomes bigger than a given value, then we can switch to the inverse. So we stop the integration of the Riccati matrix, we determine the inverse of the matrix, and we integrate further on the inverse of the Riccati matrix. It's also a Riccati equation with the matrices A and D and B and C interchanged, and then we integrate the inverse until possibly also the inverse of the matrix becomes singular, and we switch then back to the integration of the Riccati equation. So this is not really a problem, but it requires in the program, in the code, it requires the possibility to switch from the Riccati matrix to its inverse and back. If needed, if we meet a singularity, we can overcome this problem simply by switching to the inverse once the determinant has reached a certain value, and above this value we will integrate the inverse of the matrix. So this is some additional strategy which has to be taken into account. Now you may want to know whether we also can determine the eigenfunctions. So far we have only determined the eigenfrequency, and we have a Riccati matrix which has not, on first sight, which has not much to do with the eigenfunctions. So what we are interested in are also the eigenfunctions u and v. How can we get the eigenfunctions u and v in this Riccati method? Well, we determine, first of all, we determine the eigenfrequency, and we determine the Riccati matrix as a function of the independent variable. So we have First, we have to iterate and determine the eigenvalue, and once we have found the eigenvalue, then we integrate the Riccati matrix with this eigenfrequency and determine and store it at certain points in the integration interval. So we determine the function Riccati matrix as a function of the independent variable in the integration interval. Now, at the fit point, we know that the difference of the Riccati matrix from inside and outside acting on the component V of X fit has to be 0. We know that there is a solution to this equation because the determinant of R in minus R out was required to be 0 to have a solution. So we may calculate V at X fit at the fit point. So this has a solution, a non-trivial solution, and therefore and the determinant of the difference of the two matrices is 0. That means V of X fit has a solution. But I have to remind you, this is just a 2 by 2 matrix, so this can be done by hand to determine the solution of V of X fit, because in the case of radial perturbations, the Riccati matrix is a 2 by 2 complex matrix, and for the non-radial problem, Riccati matrix is a 3 by 3 matrix. So these calculations can be done by hand. These are not big matrices, but small matrices. Okay, so we have a solution, or we have the value of V at the fit point. What we do now, we solve the equation for V. V is given by U and V and the matrices C and D. We know the matrices C and D, and this is the differential equation. So it's the second half of our original system. V dash is given by C times U plus D times V. U may be written as R times V, and we know from the integration, from the first step, we know the matrix R, so we do know the matrix C, R, D, and this is an equation with coefficients which are known and are predetermined, and this is our linear equation in the part of the variables V. So this is in the radial case, this is a second order system of equations here with known coefficients, and we have a known initial condition at the fit point. So what we do, we integrate this equation from the fit point back to the boundaries. So Riccati matrix, let's say following, here is x equal to 0 and here is x equal to 1. So the Riccati matrix is integrated from the boundaries to the fit point, x fit, and this is the Riccati integration. Now we are starting, for the integration of this equation, we are starting with unique initial conditions at x fit, and we go back here with the V integration towards the boundary, because we have the unambiguous initial conditions here. Okay, so we have determined, once we have integrated this equation, we need to do this only once. Well, then we know also the Riccati matrix, we know V in the entire integration interval, we know the Riccati matrix, and so by U is equal to Riccati matrix times V, we also have the component U. Okay? So the important thing is that we need to specify, for this integration, we need to specify the Riccati matrix from the beginning. We cannot integrate the Riccati equation simultaneously with this equation. because that would again become numerically unstable. So what we have to do, we have consecutively, we have to determine first the eigenfrequency, the Riccati matrix, and then with the known Riccati matrix, we have to integrate the V component back to the boundaries. And then with the V component and the known Riccati matrix, we have both U and V. So that's the way how to determine the eigenfunctions in the Riccati method. Okay, finally we have U is equal to R times V, and we have completed the determination of the eigenfunctions. So we do not only get a stable procedure to calculate the eigenfrequencies, we can also determine the eigenfunctions. So we have everything. Okay? Well, the Riccati method is very reliable because you can determine the final result of the Riccati method is a complex function whose zeros are the eigenfrequencies. You can consider, or you can investigate the surrounding of a zero, and therefore you can check whether your eigenfrequency is a numerical artifact or whether it's a physical eigenfrequency. You always have control over the determination of your eigenfrequency. So it's pretty reliable, and you can always at each step you can check whether your numerical procedure works or gives you fake results, or whether the results are physically meaningful. The second advantage of the Riccati method is that you can achieve an extremely high accuracy because it's a shooting method, and the accuracy of the integration can be controlled locally to meet any prescribed accuracy for the integration, and also of the iteration of the eigenfrequency in the end can then be done with predefined accuracies. So the method is particularly well designed for eigenvalue problems which require a high accuracy. And I would have liked to show you one of the most demanding eigenvalues problems we have encountered. This is taken from fluid mechanics, and it's a very basic problem in fluid mechanics. It's the stability of the so-called Poiseuille flow. Poiseuille flow is the flow through a pipe, or in an idealized case, it's the flow between two planes, which is generated by a pressure gradient. Either you have a very simple configuration, you have a pipe and you have a pressure gradient, you have a higher pressure on top than on the bottom, and then the flow will be initiated through the pipe, and it will have a parabolic profile. This flow does not stay a laminar flow. It does not continue with a parabolic profile, but it becomes turbulent. And the big question in fluid mechanics is, when does this flow become turbulent? And for this reason, we do a stability analysis, and we consider, or we investigate, the stability of this flow. Now, this is a very simple problem, and the stability problem and the question, when does this flow become unstable, what is the typical Reynolds number when this flow becomes unstable, is a very old problem. It was posed the first time by Orr and Sommerfeld in the end of the 19th century. So the problem is more than 100 years old, but it took almost 80 years to solve the stability problem and to tell people what is the Reynolds number above which this flow becomes unstable. So it is very hard, it's an extremely hard boundary eigenvalue problem of fourth order, very similar to our stellar pulsation problems. This is also fourth order. So this stability problem leads to a fourth order boundary eigenvalue problems, very similar to that which we consider in the framework of astrophysics. So 80 years, only in the 1970s, the first reliable numerical calculations have been done to determine the critical Reynolds number for this flow. I would have liked to show you that you can do it actually with the Riccati method with not very much effort. You don't need big matrices, nothing. You take the Riccati method, you put in this fourth order equation in the same way as we do it for the radial and the non-radial perturbations, and we get extremely accurate results comparable to the latest results which were obtained using Chebyshev approximations, and so very sophisticated mathematics was applied to determine this critical Reynolds number. If you plug it in your Riccati formulas, you immediately get the highly accurate results. I will not have the time to show this to you. If you are interested, the rest of the transparencies contains this example for treatment of stability, highly demanding stability problem with the Riccati method. Okay, but one thing I want to mention with this is, where does this singular solution of the Riccati method come from? Since we had to switch from the Riccati matrix to its inverse here, but what is the reason for the singularities of the Riccati equation, or the solutions of the Riccati equations to occur? Okay, let's consider a very simple equation which we can represent, or which we can write as a Riccati equation. Let's consider a harmonic oscillator. The second derivative of u is given by minus kx. This is the equation for the harmonic oscillator. You know the solution. What is the solution of the harmonic oscillator? What do you see? It's an oscillator, so sine and cosine is the solution of this equation. So a second order equation, and we may rewrite it in terms of a first order, of a system of first order. So we write u dash is equal to v. We introduce a new variable, then v dash, this is the second derivative, is given by minus ku. Well, we have already taken the right notation. We have taken u and v. So this is maybe written as u dash is equal to a times u plus b times v, and v dash may be written as c times u plus d times v. This is the first step in a Riccati treatment. A is now not a matrix. It's a 1-by-1 matrix rather than a 2-by-2 matrix in the case of a fourth order system. And we read off from the comparison of these two equations that B is equal to 1, it's V, C is minus K, A and D are 0. So our famous harmonic oscillator may be written in terms of a Riccati equation, and we can explicitly write down the Riccati equation here. So we know that R dash is equal to B plus AR minus RD minus RCR. A and D are 0, B is 1, so this is 1 minus KR squared. This is a nonlinear equation with regular coefficients. Well, and we know the solution of the original equation, the second derivative of u is minus kx, so we have cosine square root of k and sine square root of k as a solution of the equation. So we know that u and v are given by cosine and sine alpha t, where alpha is square root of k. So u, the most general solution for the harmonic oscillator is C1 cosine squared k times t plus C2 times sine square root k of t. V is the derivative of u, so v is u dashed, this is square root of k. We simply differentiate the cosine and sine, and we get the sine and cosine instead here. Okay, now we know the Riccati variable, so to say the solution of this equation, the solution of this nonlinear equation, which is simply the Riccati matrix is simply the ratio of u and v. In this case, r is u over v, and we know u and v here. So we are left with the Riccati variable is given by, in the nominator, the cosine and sine term, and in the denominator we have minus sine and cosine. Well, this function here can have zeros. So we have singularities. If we choose square root of k and the integration constants appropriately, then the denominator will have zeros, and we will have singularities, which are not caused by some numerical effect. This is simply because the solution of the Riccati equation has singular solutions. That's a little bit surprising. We have a well-behaved equation, the Riccati equation. The coefficients of the Riccati equations do not have any singularity, nor do the initial conditions have any singularities or so. The only point is that this equation is nonlinear is a nonlinear equation, and this produces, for the solutions, it produces singularities, and these are genuine singularities. They cannot be removed by any trick or any numerics. If we want to calculate this numerically and we are not aware of these singularities, then we will make big errors if we just cross these singularities, because we cannot handle singularities numerically, but the solution of this equation has genuine singularities. We have to be aware of these singularities. What we do, we switch in our approach. We switch to the inverse, which then of course has a zero. So we can integrate simply by switching from the Riccati variable to its inverse. And that's where the singularities come from. They are not some mathematical or numerical artifacts. They are genuine singularities of the nonlinear equation. For a linear equation with regular coefficients, we would never get such a behavior. Linear equations, once they are well behaved, once they have no singular points, or if the coefficients remain regular and finite, we will always have finite solutions. This is not true for a nonlinear equation. Okay, that's just to demonstrate how these singularities are introduced here in the Riccati formalism. Okay, now if you are interested in this stability problem, well, I'm afraid that we will run out of time. Once we have some time left, I will come back to this and I will explain you in detail the solution of the Orr-Sommerfeld equation using the Riccati method, and at the same time solving the stability problem of the pipe flow or the plane and circular Poiseuille flow. Let me just show you this is the problem. Well, we have a pressure P1 and P2, and this pressure causes the fluid to flow between these two boundaries. It has a parabolic profile, and once you increase the pressure over a certain threshold, or in other words, if the flow speed becomes too high, then this flow becomes unstable. It switches to turbulence, switches to become turbulent, and the onset of turbulence is the problem we want to solve. We want to know when does this flow become unstable, what is the typical Reynolds number above which we have turbulence for that flow. The Reynolds number is of the order of 5,000, and you can determine this using the Riccati method very precisely to 5,772 point something. Okay, so the Riccati method can be used to determine this very demanding, long-standing problem of fluid mechanics. Okay, so let's now close this session about the numerics of the linear stability problem, and let's come to another topic which we have already touched a little bit. So this is then the next file on the adiabatic approximation. Okay, we have in one of yesterday's lectures, we have considered, or we have discussed the coefficient C1, which appears in the perturbation equations. The coefficient C1s we have seen is essentially the ratio, or denotes essentially the ratio of the thermal timescale to the dynamical timescale within the star, and the coefficient is, apart from being large in the center, it also diverges in the center, and this requires an irregularity condition which is identical with the requirement that the changes of state have to be adiabatic. So the boundary condition at the very center of the star, the regularity requires adiabatic changes of state. And even if we get close to the boundary, to the inner boundary, this coefficient C1 becomes very large because thermal timescale becomes big, and this means thermal timescale becoming large means that a mass element cannot exchange heat with its surroundings, and therefore its entropy has to be constant, or the equations of the changes of state have to proceed adiabatically. Well, now we saw that for the ratio of thermal and dynamical timescale becomes smaller if we approach the surface of the star, but this is different for different stellar models. You have different behavior, so we consider the Cepheid and the hydrogen deficient carbon star. So in this part of the star where the ratio of thermal timescale to dynamical timescale is big, we have this forces us to have adiabatic changes of state. This is no longer true if you go close to the surface. Now, for the Cepheid, the domain where we have small thermal timescale is small compared to the domain where the thermal timescale is big. This is not true to the same degree for a hydrogen deficient carbon star. In the inner part, again, thermal timescales are large. In the outer part, or in a larger fraction of the outer part, the thermal timescales are small. But for those stars where this region of low thermal timescales is small, we may try to apply the adiabatic approximation, or we may apply or assume adiabatic changes of state for the entire star. Of course, for the inner part, it will be okay. It's justified. But the question is, do we also get a reasonable approximation to the problem if the domain or the region where thermal timescales are small are negligible or small in our star? This might be the case, or we might think that this could be the case for a Cepheid. It's certainly not true for a hydrogen deficient carbon star. Or if we compare the other two stars, for the 60 solar mass star, the domain where the thermal timescale to dynamical timescale falls below unity is only a few percent in the star. It's only at most at the outermost 10%, whereas for the 24 solar mass, it is almost half of the star, where the timescale, the thermal timescale, is smaller than the dynamical timescale. Okay, so for the 60 solar mass star, we may try to apply the adiabatic approximation all over the star, and we could then compare the results of the full non-adiabatic analysis with the result of the adiabatic analysis. Okay, that has been done already yesterday, and so we can start off from the results of yesterday's lecture. Well, the consequence of requiring adiabatic changes of state, or the Lagrangian perturbation of entropy to vanish, is that the equation of state, which might be formulated either in terms of the pressure as a function of entropy and temperature, or the pressure as a function of pressure of entropy and density, then reduces for s equal constants to p as a function of t, or p as a function of rho. And once we differentiate it and go to the Lagrangian perturbation of pressure and pressure, density, and temperature, we end up either with delta P is proportional to nabla adiabatic in the case of delta T, or being proportional to gamma adiabatic times the relative change of density or temperature respectively. Or in terms of relative changes, which are used in the perturbation equation, that the relative change of temperature is given by nabla adiabatic times P. That has been discussed already yesterday, and we also saw that in this case the thermal and the mechanical equations decouple and only the mechanics remains left. That's the result of yesterday. We have a reduction in the order of the differential system. We end up with a second order system, and only sigma squared appears in the equation. Apart from sigma squared, all coefficients are real. There is no complex coefficient left. Well, the sigma squared is the term which is associated with the mechanical acceleration. Okay, that has been seen yesterday. Well, we require for validity, as discussed yesterday and just a few minutes before, that adiabatic approximation is always valid in the stellar interior. Deviations from adiabaticity are only found in the outer envelope, and whether the adiabatic approximation is satisfactory or is expected to be satisfactory depends on this particular stellar model. Cepheid seems to be well suited for the adiabatic approximation. Hydrogen deficient carbon star does not seem that suitable for the adiabatic approximation. Okay, so we are left with, in the end, with the equations we have already discussed. These are okay, we are left with the following equations. Well, these were the equations we were left yesterday. This is the mass conservation equation. This is the momentum conservation equation. And we have two boundary conditions: the remaining regularity condition at the center and the force-free boundary condition at the surface. Okay, this is the system which we are left in the adiabatic approximation. Now I have to go back a little bit, and I have to quote a theorem, a famous theorem. The adiabatic perturbation problem is, both for radial and non-radial perturbation, is self-adjoint. Self-adjoint means that the eigen frequencies or the eigenvalues are real here, meaning that sigma squared is real. So without proof, the adiabatic perturbation problem is a self-adjoint problem, with the consequence that sigma squared, taking sigma squared as the eigenvalue, sigma squared is real. We will see this explicitly for the radial case later on. We will automatically end up with a proof for self-adjointness and real sigma squared, whereas the proof for non-radial perturbation is somewhat more involved, and I don't want to get through all the algebra and the mathematics to prove that even the non-radial problem, the non-radial adiabatic problem, is self-adjoint and and leads to real values of sigma squared. Now, what does this mean for our system? So sigma squared is real, and then we can decide or can distinguish between positive and negative values of sigma squared. If sigma squared is positive, the root of sigma squared is real, and we have plus minus sigma r, real part of the eigenfrequency. That means we have an oscillatory, neutrally stable situation. Sigma I is 0 in that case. The other case is if sigma squared is smaller than 0, then the solution of this equation is imaginary, so the solutions will be plus minus I sigma I. We have no oscillation, sigma r is 0. We have a non-oscillatory instability and damping at the same time, because note that the negative values of sigma I mean excitation or instability, and positive value means damping. So we have always a pair of unstable and damped modes. They come always in pairs of a stable and an unstable mode, and they are non-oscillatory, so they don't oscillate. So we have, in that case, an unstable and a damped, exponentially growing or decaying mode. Both come at the same time. So either if the star is to be stable, then it has to be neutrally stable. No, the sigma I is 0. It only has a frequency, and the amplitude of the pulsation or of the oscillation will not change. Neutrally stable, no change in the amplitude, or if it is unstable, it has a damped counterpart, and it is a non-oscillatory instability. Okay, adiabatic instability is always exponential, non-oscillatory, and occurs once the sigma squared, once the square of the eigenfrequency becomes negative. Sigma squared has to stay neutral, has to stay real quantity. Okay, so now this is what we get from our consideration, from considering the adiabatic limit of the non-adiabatic system. Well, this is not the conventional, not the standard form of the perturbation equation which is usually used. In order to end up with a standard equation for radial adiabatic perturbations, we have to transform this system. We have to transform it into a single differential equation of second order. We have to transform the independent variables back from log P naught to the radius, and well, okay, the first step would then be to transform the independent variable. So far we have log P naught as the independent variable, and the transformation from P naught to R can be done using the definition of our coefficient C4, or by applying the hydrostatic equilibrium. D log P naught by d log R is nothing but the pressure gradient in the equilibrium between gravity and pressure gradient. So we have d log P naught over d log R is minus 1 over C4, and this is given explicitly by density, pressure, and the gravitational potential energy. So the derivatives with respect to log P naught, which are contained in the above equations, can be rewritten d in terms of the derivative with respect to r by d log P naught is minus C4 times r times d by dr. Okay, we do this transformation, then we eliminate the pressure perturbation and we keep the Lagrangian displacement. So we try to get rid of the pressure, and we express our perturbation problem only in terms of the Lagrangian displacement, obtaining a second order equation for the Lagrangian displacement. Okay, so now of course we also have to insert the definitions of C3 and C4, and after some algebra, if we do that, after some algebra, we are left with the following standard form of the radial adiabatic wave equation. Okay, I don't want to go through all the algebra and all the mathematics. If you're interested, you can try with these instructions, you can try to arrive at this equation doing after some algebra. Okay, this equation is of second order. There are two derivatives with respect to the radius of the Lagrangian displacement, and this differential operator is a differentiation onto a term which contains first some quantities of the background model, which is the adiabatic index, the pressure, and the radius to the fourth, and this acts on the this function times the derivative of the Lagrangian displacement has to be differentiated. So this is the differential operator which is contained in the final equation, plus zeta times a bracketed term which contains in the first place the sigma squared and some function including the density stratification and the radius, and the second function containing the pressure stratification and the adiabatic index. We see that the function f and g, this is denoted by function f, is bigger than 0, and also the function g is bigger than 0. So this is the standard form of the radial adiabatic perturbation equation, second order perturbation equation. Of course, we have to transform also the boundary conditions. At the outer radius, at the surface of the star, we have that the pressure perturbation has to be 0. In terms of the Lagrangian displacement, this condition can be rewritten as r times d zeta by dr plus 3 zeta is equal to 0. And at the center, again, we have a regularity condition. You see, for instance, at the center, this coefficient will vanish. So this is a singular point, and this requires a regularity condition also for this equation. Okay, now how shall we proceed further? Well, first of all, the physically relevant quantities which enter this equation is the density stratification. If we look here, that's the density stratification, the pressure stratification, and as an important additional quantity, the adiabatic index. This means one of these indices coming from thermodynamics, denoting the d log p by d log rho at constant entropy. These are the three quantities which determine or which are essential for the radial adiabatic perturbation problem. Now we identify the Lagrangian displacement with y, and we identify our eigenfrequency squared, sigma squared, with lambda. Then we can write this equation in a form which is very well known in mathematical physics. This is a so-called Sturm-Liouville equation. Well, the derivative of f times the derivative of y dash That is simply the first term of the adiabatic wave equation. So the derivative of f times the derivative of zeta, this is the first term, plus y times, y denotes the zeta, times the eigenfrequency, this is sigma squared, times the positive function g plus a function h is equal to 0, with the condition that f and g has to be a positive function. So this is a Sturm-Liouville equation, and this has been thoroughly discussed by many mathematicians in the end of the 19th century and in the 20th century. And we can take any of the properties of this Sturm-Liouville problem and transfer these properties to our linear adiabatic wave equation. Well, let's first of all study the property of the differential operator. We will come to the general properties of Sturm-Liouville equation later, but some of the properties we should convince ourselves in detail. So what we do, we take the operator, the differential operator occurring in the linear adiabatic wave equation, that is d by dr gamma adiabatic p naught times r to the fourth, acting now on a function on a Lagrangian displacement which we denote by zeta 1. We multiply this differential operator acting on zeta 1 with the function zeta 2 and integrate the entire quantity over the integration interval, that means from 0 to the surface. Now we perform a partial integration by putting this derivative onto the zeta 2. Then we have boundary term, which is zeta 2 times this factor times d zeta 1 by dr. This has to be evaluated between 0 and r. Now at the radius r, p naught is 0 or close to 0, and at r equal to 0, the term r to the fourth is 0. So this boundary term vanishes, and we are left with minus. The derivative is now put to the zeta 2, is d zeta 2 times the function gamma p times r to the fourth times d zeta 1 by dr. Now we again perform a partial integration and put this derivative onto the rest of the integrand. Then we get again a boundary term. The boundary term now looks like minus d zeta 2 by dr gamma adiabatic p r to the fourth times zeta between 0 and r, and again at the outer boundary pressure vanishes, at the inner boundary the r to the fourth vanishes. That means the boundary term vanishes again, and we are left now with the rest of it. This is d by dr. So this derivative has been put on this term. So we are left with zeta 1 and the derivative of d zeta 2 by dr gamma adiabatic p naught r to the fourth with the sign changed. So what we get at the end is the final result is the integral over zeta 2 with a differential operator acting on zeta 1 is equal to zeta 1 and the differential operator acting on zeta 2. So this operator is said to be symmetric, or in mathematical more elegant way, it's a self-adjoint operator. What does it mean? If this differential operator is symmetric or self-adjoint, well, let's abbreviate this differential operator with d acting on zeta, and let's consider the following integral. So we take the integral of zeta star. Star should denote the complex conjugate. So we multiply the operator d or acting on zeta with the complex conjugate of the function zeta, integrate over the interval and take the complex conjugate of this quantity. Well, the operator d is real, and the only complex quantity appearing under this integral are the eigenfunction or are the functions zeta. So taking the complex conjugate, this will give the original value complex zeta twice complex conjugated gives the zeta itself times d acting on zeta star. Well, because this operator is found to be symmetric, this is equal to zeta star times d times zeta. And this means if we compare this quantity with that one, well, the complex conjugate of this quantity is equal to the quantity itself. What does it mean? It's a real quantity. So this integral is real. Well, if we now consider the complete equation, we multiply the equation, the linear adiabatic wave equation, with a complex conjugate of zeta and integrate over the volume, then we are left with zeta integral over zeta star d acting on zeta plus sigma squared integral over the function g zeta star times zeta plus integral over the function r zeta star times zeta dr is 0. This is simply integrating, multiplying the equation with the function zeta and integrating over the volume or over the integration interval. Then we know, well, this quantity we know is real. Well, zeta star times zeta is the modulus of zeta squared. So this is a real quantity, g is real, and all the same is true for h and zeta star times zeta. So this is real, that is real. So sigma squared has to be real. That's what we have proven explicitly now for the radial system, that the differential operator is self-adjoint and sigma squared therefore is real. So we have proven self-adjointness and reality of the eigenfrequency sigma or of the eigenvalue sigma squared. Okay, that means sigma squared, we have explicitly shown eigenvalues sigma squared are real. And that's what we have used before to show that instabilities in adiabatic regime are exponential, and if a star is to be stable, it has to have neutrally stable oscillatory mode. Instabilities are never oscillatory, they are exponential and also come with a damped counterpart. Okay, shall we make a break here? And after the break, we will show some other properties of the linear adiabatic system, radial linear adiabatic system.